Thank you very much to Oma. Where did you go for giving this opportunity? Appreciate it. So I'll be talking about privacy preserving machine learning today and some of the cryptography that goes behind it. So it's not related to blockchains. I'm going to give a very high level overview of this, just to kind of encourage, hopefully encourage some of you to look closer into this. As always, when you start looking into the cryptography, there are more details, more interesting details underneath. And a success would be if anyone would actually go and read some of the papers that I'll put a reference to during the talk. If that happens, that will be amazing. Okay, so as always, the first question is often why? Why are we doing this? And one way of framing that is to try to look at what a company that wants to offer or that wants to build a machine learning service, what problems they might run into. So let's see what that service looks like. So let's say we have a company here. They want to train this prediction service here on the right. What they would typically do is they would collect a data set. They would run that data set through a training process, ending up with a prediction model. But of course, that exists in a context, and that context could be how do we get this data set here on the left? And they might build that internally. It might be data they already have, but it could also be that they need to go to external parties and actually get this data. So there's these public data sets called ImageNet, for instance, that they might go to. They could also go to specialists or experts to somehow build a data set over the years, or they could go to companies that are willing to sell the data set in exchange for some value, of course. Then, on the other hand, over on this side, we also have, when they have the model or the prediction service, they probably want to use it for something. And again, it could be internal purposes, but sometimes it would also be that they want to offer this as an external service to customers or clients. All right, so as a concrete use case of this, a group of researchers, I guess about 2 years ago now, developed this skin cancer image analysis network. So the way they worked is they developed a mobile app that would take a photo of a skin lesion. Then the user here could send this through what's called a convolutional neural network and get back a prediction about whether or not this skin lesion was potentially cancerous and needed further inspection. The way they built that system was they went to a bunch of dermatologists. They asked them to provide these clinical photos that was already labeled about whether or not this was, what kind of skin lesion this was. They ran it through a process called transfer learning, and then they ended up with this convolutional neural network. What they managed to do with this was they managed to build expert level classification systems. So what this means is that now everyone that has a mobile phone potentially has an expert dermatologist in their pocket and could go around and do an inspection whenever they wanted to. So out of a fear of stating the obvious, or with a fear of stating the obvious, as soon as we can start to build systems on this sensitive information, we can have a very big impact on, or machine learning could have a very big impact on society. But of course, when we start to do that, there's also some problems. And one way of facing that problem, or phrasing that problem, is in terms of privacy. And more particularly, we can see there's potential bottlenecks that might exist in this process. So if we go back to the process that the company is trying to run through, the first one might be that they can't get access to this training data needed in the first place. So maybe the dermatologists are not willing to give these clinical images away out of either liability, maybe the company that's willing to sell the data, since they don't control how the data is being used afterwards, they're charging a high price that the company can't afford to pay. So in other words, maybe the company is stuck already getting the data in the first place. If they manage to get the data, they could also run into this risk management, like how do you hold on to this sensitive data? It could be that they're liable for this. If there is a leakage, they could be in big trouble. So they might say, okay, we can get the data, but there's no way we want the data because it's too toxic, to use that word. Even if they manage to make the service, they also need to incentivize users to actually use this service. So again, if you're using a service where you're sending a photo of you that tells everyone whether or not you have potential skin cancer, maybe you don't want to use that service out of a fear of what the company will do with that data. So they might have a good model, but no one wants to use it. And then finally, there's another bottleneck where what goes back to the client could potentially leak something. It could leak something about the initial training data, but it could also leak something about this model they have. So if this model represents high IP, maybe they want to prevent what's actually going on here. All right. So one technique for trying to mitigate some of these issues and actually allowing us to build these systems in the first place is what's called differential privacy. Some of you may have heard of this. The way it works is that as part of this training process, or as part of the prediction process, we're going to add some noise into the data. And that noise kind of takes care of hiding any individual private information in the data set. So the way I'll call this now is I'll call it a sanitized data set. So in other words, what they get from the external data providers on the left could already be a sanitized data set that doesn't leak too much privacy. So the patients, for instance, that was part of the clinical photos over here, there's no personal information leaked in them. You can't re-identify users and so on. Then the company, when they run the prediction, they could also insist that the users adding some noise to the prediction input before they run it through the model. So in other words, the company can see the data, but maybe somehow it doesn't leak too much. What would happen then is that the risk management down here is maybe mitigated because now the company is just seeing sanitized impersonal data. The leakage over here could also be controlled because the model that was trained on the training data doesn't leak anything about the initial training set. However, users, so they might want to use the service now, but I'm only putting it in orange here because maybe the accuracy that they can now get from the prediction is not high enough. Maybe this noise actually kills kind of the usefulness of this model in the first place. And also, maybe they can't get access to high quality data if this data has to be noised. So it's not a perfect solution, this thing. And
So if we're talking about dithering, from the perspective of signal processing, communication theories on dithering, taking information such as they usually do it for like an A to D, when you know analog device.
שינו את המיקרופון השני, וכל מי שרוצה לדבר שינו את המיקרופון.
So you add this dithering, sort of just to make the analog voltage different, and then instead of a line, you will get a difference that it's really not a line, it's something like this. And if you plan it really good, then you have both property of not affecting the final result, and also getting more information, really.
so the way the noise is added to, so the question is around, is this similar to what you could do in digital signal processing to add noise into the process? One difference here is that this is...
Dithering is not for noise, it's actually
modifying.
Design noise, it's like stereo revenue.
Right, okay. So you do have to add specific noise to this. So it would have to be drawn from a Gaussian process or Laplacian process or something like this. So this one is, the properties of this is based on, it's a formal framework where you can guarantee that not too much is leaked, or you can kind of quantify how much is leaked. So this is, in other words, this is based in a mathematical definition that kind of gives you an idea of what is, okay. But actually, I'm not going to talk about this at all. So because there's another technique, which is then this secure computation thing. And secure computation doesn't add noise to the process. It just moves the process into encrypted space. Okay, so let's see what happens then. So what we can do is we can say, instead of getting the data set in the plain text form, we're now going to get an encrypted data set. And then using this secure computation, we can compute on this data set. We can run it through the training process without actually decrypting in between. And then we end up with potentially an encrypted model that we can decrypt, or we can continue with that. But likewise, the users, when they send a new prediction input, that one can also be encrypted and run through the model in encrypted form. So at no point in this process can the company running this decrypt the data. All right. So
Training data still can be...
Oh, you're way ahead up here. Yeah. So okay. So the risk management could potentially be taken care of now, because all the company sees is encrypted data. The users would also be incentivized to use it because they're only giving encrypted data to the company. However, since one way to see it is that we're taking the original process and we're moving it into the encrypted space. So whatever leakage was in the original model is also going to be here. But assuming we can fix that, then maybe the data access issue is also okay, because data now remains encrypted. And moreover, some of the techniques that you're using for this would actually allow the companies to kind of give a control of how the data is used. So they would say, okay, this data can only be used as a training process and so on. So quick final word, to kind of get the best of both worlds, you can also do this hybrid model where you're mixing it, so you're both sanitizing for instance, the model, but also keeping it encrypted. All right, so I'm going to talk about more secure computation, and particularly about these two things called homomorphic encryption and secret sharing. I'm going to give a very rough characterization of the two. One is heavy in terms of computation. The other one is light in terms of computation. If we look at communication, they flip. Okay, so homomorphic encryption is light in terms of communication. Secret sharing is very heavy in terms of communication. They both operate essentially on integers or on bits. There are some differences there. We can go into later if anyone's interested. There's also, so one note here. I'm saying we operate on integers, but when you're doing machine learning, you typically want floating points and so on. So the way that's done is you have this fixed point encoding where you're kind of scaling your float points into an integer, and then you can operate on that. That has some implications I won't go into, but that's how we can reasonably talk about it, operating on integers. There's also another thing called garbled circuits, which kind of let's say it's a medium between the two. One downside is that it's often only operating on bits, so you have to kind of encode your data at a bits. If you want to add two encoded values, you have to have a binary adder, so it becomes more expensive and so on. And then finally, you may be familiar with secure enclaves. So this is Intel SGX, AMD, I think it's called Trust Zone, which is kind of light in terms of both. The downside is it's hardware-based, so you have to trust the hardware manufacturer and that entire ecosystem, whereas the other ones are software-based, based on cryptography. There's many different works in this field. Here's just a selection of them. The tendency here is to actually mix some of these technologies. So if you look at neural networks, for instance, you would typically have these different layers. I'll go into more details in a bit. But you might use one technology for one layer. For the next layer, you switch to another one, and so on. The trick is really how do you get the best performance, and there could be a mix of these, as you can see here. All right, so let's do the simplest possible model we can do. Let's try to do a prediction using a linear model. What happens in that is we have a model over here with some weights, some vector W, and we have a user over here with some vector X. He sends the X to the prediction service. The prediction service computes the dot product, send it back to the user. All right, let's unfold this. So we see the dot product, in case anyone doesn't remember. We just do the point-wise or the component-wise multiplication, and then we add everything up afterwards. All right, and then that's going to give us a scalar value, which is now our prediction. If we want to do this in a secure space, so let's try to see how we can do that using homomorphic encryption. Now the user here is going to have the private decryption key, and we assume that the public decryption key has already been shared. He's going to encrypt this input, send it to the service. The service can now somehow, going to look into that, compute this dot product, but without decrypting, so sending back an encryption of the dot product that the user can decrypt and learn the result. If we plug it into our formula, we see we now have these components, which part of it is encrypted. If we can somehow move this W1, for instance, into the encryption of X1, then we're going to say that's a public multiplication because W is public. So we end up with an encryption of X1 times W1, for instance. Then we also need to do this addition. So we have 3 ciphertexts now. We need to add them all together and get an encryption of the sum. If we can do that, then since it's operating on 2 ciphertexts now, I'm going to call that a private addition. Okay. So if we're using a normal encryption scheme here, so think RSA, even elective curves and so on, we don't know how to do this, so maybe that's no surprise. So in particular, we need this thing called a morphic encryption scheme. Okay, so that's an encryption scheme that satisfies these 2 properties that allows us to manipulate ciphertext in this way. All right, moreover, maybe this is obvious for all of you, we need this encryption scheme to be probabilistic. So besides encrypting a plain text value, we also have this randomness component. What happens is that, so let's say the prediction is just a 0 or 1, whether or not this was a cancerous skin lesion. If we didn't have this randomness component, someone could brute force it, right? So without even knowing the decryption key, he could make an encryption of 0, make an encryption of 1, see if it matches with the prediction. If we have this randomness component, then he has to brute force not only the plain text, but also this R. So if there's sufficiently many choices of R, then he won't be able to do that. One particular homomorphic encryption scheme is called the Paillier scheme. So this is about 20 years old now, actually. 10 years ago, there was a new kind of generation of encryption schemes, or homomorphic encryption schemes being invented. They're a bit harder to explain, so I'm going to take this more basic one. It's still used, you still see it in some of the papers, but the other ones are a bit more powerful, maybe even a bit more interesting from a cryptographic perspective. So the way it works is, this is how you encrypt your R and your X. It looks a bit tricky, but if we break it down, the first thing we see is we now have this blue component, which is the public encryption key, consisting of these 3 values. The first thing we do is we take our G, which is an integer, and we raise it to X, which is also an integer. Remember, we have the fixed point encoding. We do the same for R and N. We multiply the 2, and then we do everything mod N squared. Okay, so we can do this. That's not unreasonable. If we do a quick example, let's say G is 36, N is 35, N squared is whatever it is. And we want to encrypt 5 using randomness 2. We plug it into a formula, we get this. If we encrypt 5 again using a different randomness, then of course we get a different ciphertext. Okay. So some of you may be familiar with the RSA encryption system. This N here is actually an modulus from an RSA system. So in order for this to be secure, these values will typically be around 4,000 bits long. So even if we're operating on relatively small values, we're now having 4,000 bits values here. So there's some hints of where the computational complexity starts to kick in, as opposed to computing on plain text values. All right, so let's see how we can do private addition first. So these are one of the operations we need to do in Paillier. Let's say we have two ciphertexts. If we multiply them, we plug it into our formula, we rearrange, and we see this is exactly the same as if we had encrypted x plus y using randomness r times s. All right, so take two ciphertexts, multiply them, and that gives you a ciphertext of the sum. We can take our two ciphertexts from before. We see this gives us an encryption of 10 using randomness 8. The other operation we needed was to do public multiplication. So let's see what happens if we take an encryption of x and we raise it to w, where w again is an integer. We plug it into a formula, we rearrange, and we see we get the same as if we had encrypted x times w using randomness r to the power of w. We plug it into a formula, we see we get an encryption of 10, so 5 times 2, using randomness 4, 2 squared. All right, so with these two operations, we can actually do a prediction using a linear regression model without decrypting the data in between. If we then instead look at secret sharing, the difference here is, so now we're moving to another technology. There is no decryption key now. So instead of having a trust assumption that says no one knows my decryption key, we're now going to make a trust assumption that says I have two independent servers and I trust that they don't collaborate beyond what I expect them to do, or what I expect them to collaborate on. Maybe it's not clear, so it's not always clear how you could find these two servers. It could be that the client is actually acting as one of the servers. It could be that there's a company that's running one server, a union of dermatologists, for instance, running the other server. This is one of the things you have to kind of answer if you want to use these techniques. If we can do that, however, we can now generate a share of our input, so a share 1, share 2. We can send that to a server. These has the properties that if you only know one of the shares, then it doesn't leak anything about X in this case. However, they can still compute on it, and they can send back a share of the dot product that we needed to. Knowing both shares on the client side now, he can reconstruct and then learn the dot product. And of course, we need this also to be homomorphic, so we still have these two operations we need to do. And we can say, okay, if we can do this, then this is a homomorphic secret sharing scheme. All right, so one particular instance of that is what's used in the speech protocol. It's also called additive secret share. We still have this blue component here, but now it's no longer a public key. Now it's a public parameter. What that means is it can be fixed for once and for all, to supporting the application, and it can be. It doesn't have to be any size constraints. It just has to be supporting whatever precision we want for our numbers. Then the first share is just going to be the randomness that goes into it. This obviously doesn't leak anything about X, because if it's picked independently. And the second share is going to be our X masked by this R, blinded by this R. So if you don't know R, then this essentially looks like a completely random value. It doesn't leak anything about X. But of course, if you know both, you can add it up and you get back X. As a quick example, if our M is 10, we want to share 5 using randomness 7. The first share is 7. Second share is 5 minus 7, minus 2. Minus 2 mod 10 is 8. And if we add back together 7 and 8, we get 15. 15 mod 10 is 5. So we know how to reconstruct. The first operation we had to do, again, was private addition. So let's say we have our two servers. They already have a sharing of X. They already have a sharing of Y, in the case of these 4 values. And now we want to define the set 1 and the set 2 that adds up to X plus Y. Turns out they can just add what they already have. Okay, so they define the set 1, set 2 in this way. And if you rearrange, you'll see this set 1, set 2 adds up to X plus Y. The other operation we need is public multiplication. So again, we already have a sharing of X. Both servers know this W. They can just multiply what they already have, defines a set 1, set 2. If we rearrange, we see this adds up to X times W. So with these things, we also know how to do a prediction using a linear model, using secret sharing. Note that these values here, there was no interaction here, so this was entirely local computations. And since these values can be relatively small, this is no more expensive than if we had done this basically on plain text data. It comes when we want to look at more advanced stuff. Yeah.
You showed the inference part of linear regression. How does it work for training the model, for getting the W vector when you only have encrypted training data?
Excellent question. So this is only for predictions. I'll say a few words about how we can do training afterwards. For now, I'm kind of assuming that the training has already been done, and what we're interested in protecting is the client as he sends his input. But I'll have a few slides on that as well. Okay, so let's try something more advanced. Let's try to do digit classification using convolutional neural networks. So in this case, we now still have a model. It now has significantly more weights, and now the user has this kind of image instead. So this is called the MNIST example. So it's very relatively simple images. He sends them to the model, and he gets back the whatever digit the model predicted to be inside this image. All right. So the way this works is we're using these things, CNNs. Don't worry too much about what they do. This is typically what you would do in a neural network. So you have a few layers having certain operations. The top layers here are typically called feature layers, and then the last ones are called classification layers. But yeah, this, with some knowledge in machine learning, this should not be too surprising. They've been very successful recently in various tasks and so on. All right, so the first question is, how do we secret share images? Keep in mind that an image is just an array of numbers. So of course we can also generate random looking images like this. That will be a first share. Likewise, we can use it to blind the image, so that will be a second share. And again, of course, if we add these two images together, we recover the original. So when we want to run a prediction through the image, what happens is that we now have a vector that represents our input. We're now going to run it through these layers from top to bottom. This convolutional layer is essentially just the dot product. Okay, so that's basically what we had in the previous slides. If we can do that, then we can do the convolutional layers. Same for the dense layers, basically just the matrix multiplication or dot product. The dropout layers are just dropping some values. That's kind of independent of even if we're using encryption or not. Then we could continue. So some of these layers, the activation layers in particular, would essentially require us to compare encrypted values, which is relatively expensive. We can do it, but it will be relatively expensive. Turns out it's cheaper to actually switch to another type of layer, so another what's called an activation function. And likewise, this pulling layer we have here is going to compute the max pulling. So it's going to look at a small region in the image, and then it's going to find the max value in that region. Again, that's a comparison, which is expensive. So it turns out we can actually get significant increase in speed if we are willing to replace these layers with slightly different layers. So that's what I've been doing here. So now I'm taking, instead of having this ReLU layer, I'm going to take what's called a sigmoid layer. And instead of having a max pulling layer, I'm going to take an average pulling layer. So an average pulling layer is just adding up whatever section of this image is looking at, and then it's dividing by how many elements is added. That division is much cheaper than what we would have done if we'd used some of the other techniques, because it's happening, we already know what the divisor is. It's a public value. So if we believe we can do that, then we can take care of all these layers. Now, there is one layer down here which is called the softmax, and the softmax can be done as well, but it's quite expensive. What we could do if we're just doing predictions is we could move it to the client. So we're going to say, when we run through the layer, the input remains encrypted. When we get to the last layer, instead of sending him the output of that layer, we send him the input of that layer. Then he reconstructs the inputs and he applies the softmax if he wants, after he reconstructed locally on the device. Or maybe he doesn't need to apply the softmax. Maybe he's just interested in seeing what was the most likely classification, and then he just takes the highest value. So we can kind of move that. Let's say we move that to the client. The key takeaway here, I know this gets a bit technical if you don't understand machine learning. The key takeaway here is that when you start to do this, it's not interesting to see machine learning as a black box. You really want to adapt the machine learning to the cryptography, and you want to adapt the cryptography to the machine learning, if you want good performance at least. All right, so as you were saying here, we're now replacing a comparison. We're computing this sigmoid function, and the formula for the sigmoid function here at the bottom looks much more involved, because we're now doing a division, we're raising powers, so we're raising x. X is our private value here, our secret share value. We're now using that as an exponent in this weird looking equation. Why is that not more expensive than doing a comparison? It turns out we can approximate this thing using a polynomial. So if we know that our values are only around the origin, so let's say -5 to 5 here, then we can find a good polynomial that kind of matches the sigmoid, and we can use that instead. If we do that, then instead of evaluating the formula we had before, now we just need to evaluate the polynomial. And if we look at the polynomial, then it's just a question of, we have these coefficients, these c's, that we need to multiply to some powers of x, so that's a public multiplication. And then we need to add some stuff afterwards. Well, that's a private addition, so we're already almost there. The only thing missing is, how do we get these powers of x? Because x is, again, a secret shared or an encrypted value. How do we multiply two private values together? We don't know how to do that yet. But we can do that using secret sharing, big surprise. So let's say we have our x and our y again. We now want to multiply, so we want to define a set, which is set 1 plus set 2 adds up to x times y. It turns out this is where we need communication. So this is where, if we want to do this, we need a suit server to communicate a bit. And the way it's typically done, or at least one way of doing it, is to use these things called triples, random triples. So we start out with the 3 values over here. A and B are 2 random values that's already been shared between the 2 servers. And then C is A times B, and also shared between the 2. So these have to be kind of generated before we can do this. But using them, we can define these 2 new values, alpha and beta, that doesn't leak anything about x and y, but can be used in this kind of recombination step where we define the set 1 and set 2. Don't worry too much about what it does. The main takeaway here is that we need communication, and we need to have these random triples, this kind of raw material over here. This can, but also note that this raw material is kind of independent of the computation, so it can be done in front, what's called an offline phase, and then only used later in the online phase. So you need a new triple every time you're doing a multiplication.
But you can, but you have a limited set of data, so you can get it in advance.
Exactly.
That's the key that you share.
Exactly. So that
both groups share.
Yeah. So you need the servers already have this kind of information. If when you start building this more optimized, you realize you can start streaming this data as well. So you can kind of do it in the background when you're doing other stuff. Pipelining, exactly. All right, main takeaway here is we need this raw material, but it can be moved to what's called an offline phase, and then it's already available when we reach the online phase, when we actually know shares of the data we're computing on. But then we still need a bit of communication here. However, given that, we're still using relatively simple operations. So a multiplication now just involves a few more multiplications, a few additions, but still on small values. So computation is light. All right, and with this, in principle, it's enough to do a prediction on encrypted data through a convolutional neural network. All right, so now a few words on training. I'm not going to say too much. First question is, who is the participants? So now we're going to have 2 servers running this training process. And what can happen is that the dermatologist or the experts over here, for instance, can generate secret shares of the training data and then send it to the 2 servers. Again, the question is, who's running these 2 servers? Well, it could actually be each dermatologist participating in this. So they could run their own server. It could be a union of the dermatologist and the company, or it could be 2 companies, a cloud provider and a company offering this service. This softmax that we kind of skipped before, what people would typically do instead is they will replace it with this other thing at the bottom here, using ReLUs. So I just told you ReLUs were expensive. Yeah, they're still expensive, but they're cheaper than doing the other thing. And you can actually get decent privacy, or decent accuracy, sorry, if you're using these instead. There is one paper down here that introduced this idea. People would also typically use this somewhat advanced optimization strategy. So this is how you compute the gradients when you're training your network. Again, we have this with so W here is the weights, and the weights when we're training are typically private, so they're the encrypted values. Now we have to take a square root of something that's encrypted. That's very expensive, and we have to divide afterwards using this value again. So this will be expensive to do. People typically fall back to simpler stochastic gradient descent, which doesn't really involve any of this. Another thing is you would typically use transfer learning, like these researchers did in the first use case. What this works is you start out with a network which is relatively simple, can't really do much. Then you take your public data set. That's fine. You can train as much as you want on that. That improves your network a tiny bit. Then what you do is you now fix the first layers, the first group of layers, and you say, okay, I believe they're good enough now. And then you only do the training on the last layers. So that means you have to run much less through the network. You have to do less operations and so on. This is a known technique from machine learning. It can give you good accuracy. All right. So this was all prior research. I posted some of the papers up there. One of the things I've been working on is how to make this accessible, because there's all these different cryptographic techniques that we don't necessarily understand people to expect. There's also this adaptation of the machine learning models that's non-trivial. How do we get people to actually talk together? And before saying that, there are plenty of so these are some of the papers again. There's a good comparison in the one that's linked here. There's also excellent general purpose computational frameworks or secure computation frameworks, some of them developed here in Bailan. However, they are more general purpose and they kind of require some expertise to get into, which is also why I feel like it's justified to have these more specialized projects that's actually trying to bring these two fields together. And one of them is tf-encrypted, that I'll talk about a bit about now, using TensorFlow. And then there's another one called PySift, which is doing similar things for PyTorch. All right, so again, for the why. Why is this interesting? Why these specialized projects? As I said, it is very much a mixed field. So we have cryptography on one side. There's all these different techniques we saw. You can make specialized protocols for some operations. The guarantees you give in terms of privacy have to be well defined and so on. That's on one hand. On the other hand, we have machine learning. So we saw that adapting the models can be interesting. Finding approximations to functions can be cheaper sometimes. We saw, for instance, with the Sigmoid. And also, how can we quantize data? To have what precision do we need basically for the numbers as we do the computations. So there's a machine learning aspect as well. There's also an engineering aspect. We're now dealing with distributed protocols. How do we make that efficient? How do we make sure we can use multi-core architectures, that we can scale it by essentially throwing more compute at it? And how do we build a project where it's easy to maintain the code, where we can actually read the code afterwards? And then finally, there's a data science aspect as well. How do we find use cases that works within these constrained conditions? So if you come in with your typical model and you expect this to be efficient, it probably won't be. So how can you tweak it? How can you find something that's interesting while staying within these constraints? What do you do now with the typical data science workflow when things are encrypted? So if you're used to inspecting your training data before you use it, what happens if that's only encrypted? What can you then do? And also, what happens when you start deploying these models in production? How do you monitor that they actually they not start drifting, for instance, and kind of match the real world data you get? Or when they start drifting, exactly, and react to that. So there's definitely these four disciplines involved. And one thing we don't have so far is having a common framework to discuss this in. We don't even have a common language to talk about this in.
Just a comment for this particular slide. I think you missed distributed systems as a discipline, because engineering is something like more, it's not a discipline, right?
Probably won't argue with you on that, yeah. I think it's more that you can call it computer science as well, you can call it networking and so on. But yeah, I guess it's more a classification of what you normally focus on. Yeah. Or what you know how to optimize, in other words. All right. Okay, so this tf-encrypted project, which essentially is an open source project for exploring and experimenting with this stuff in TensorFlow. For those of you that don't know TensorFlow, so it's a platform for production level training and deployment of models made by Google and backed by Google. As you can see, it's been quite popular over the last few years. It works by your computation essentially gets turned into these Dataflow Graphs. So here we have one computation. You start from the bottom actually. You give an input and then the output is defined at the top. When you build a script typically in Python, it will build a graph like this, and then you hand it over to the TensorFlow backend that will then execute the graph. So even if the interface is nice in Python, the execution is efficient in C. It has some nice benefits. So here's a tracing profile from one execution. We can see already that it figured out, without much to do on our part, to run stuff concurrently. So it's trying to take advantage of multi-core architecture. And it also figured out that when we're generating these triples to do the multiplications, that these could actually be moved up front. So we can it figured out it was more efficient, instead of generating them one at a time as we go along, to generate a batch up front and then potentially send them together. And then they're ready to use when the two servers, so that's the top two processes, would like them. just to give an example, so a main question in this is also usability, that if it's hard to use these frameworks, people won't use them. So here's an example for how you would do a public prediction using TensorFlow. If you're familiar with TensorFlow, this should look somewhat straightforward. We define some functions up here that might load the weights for a model from disk or whatever. It will take an input from the client, might do some pre-processing on this, and then when we get the final output, so that's the logics, in this case we're just going to take the argmax and then we're going to print it on screen. Then we define our model here, and we finally tell the TensorFlow backend to run it down here. So again, if you're familiar with TensorFlow, this should look straightforward. Here's what we do when we're using tf-encrypted. So when we're doing a private prediction, in this case, we're going to keep both the model weights, so the model is going to remain encrypted, and the input is going to remain encrypted as well. So what we have is, we have a model owner here who takes his weights, shares them, sends them to the two servers, and then we have a client over here that takes his input, again, shares them, sends them to two servers. And then this is how we express it using tf-encrypted. So the first thing first of all, this should hopefully look very similar to the previous script. One difference is that we're now importing tf-encrypted right next to TensorFlow, because we're not replacing TensorFlow, we're building on top of it, which also gives very high integration. As you can see, for instance, when we're processing the output, or reading the input and processing the output, we're doing the same thing as we did before. There's no change, and we're using TensorFlow for that as well. The first difference is that we now have to be very explicit about who gets to see the models or the weights of the model in plain text. Okay, so that's what we're doing here. We're saying the model owner, so that's the machine on the left here, is the only one that gets to see these weights in plain text. And the other places they will be encrypted or secret shared. The way it works under the hood is it's making sure that this function provide weights is being called on the machine of the model owner. When those weights are ready, it makes sure to secret share them, and then it sends it to the two servers. Likewise, for the prediction input, we're here saying, okay, the only one that gets to see these weights in plain text is the prediction client, and the only one that's supposed to receive the output is, again, the prediction client. And that's it. That's the kind of the key difference between those two. So as a wrap-up, privacy-preserving technologies could enable access to this new sensitive information. I don't necessarily think that we're going to move everything into the encrypted space, but if we can do so for some things, then we can start to do interesting new stuff. Secure computation is a complement to what we already have. It's not going to replace everything. As we saw as well, it can mix with differential privacy and so on. We saw that for transfer learning, we were saying, okay, let's do something in plain text without the encryption, and then only do fine-tuning in the encrypted space. It could definitely benefit from expertise in all these different fields and require adaptations on both sides. And then finally, as a bonus, there's been some interest in what's called the safety community in machine learning, where they're saying, how can we, if we have a very powerful model, how can we govern use of that model? How can we make sure that no single entity is going to take the model and run away? So using these techniques, we could split up the model, and we can say, okay, both parties have to agree on how this model is being used. So that's called governance. And also fairness. So if someone develops a model and someone else needs to test it in terms of regulatory purposes, for instance, maybe that party doesn't want to reveal his model, and maybe the other party doesn't want to reveal what he's actually testing the model on, because that could open up for gaming of the system. And with that, I'll say thank you and for your interest, and open up for questions.
How much use have you seen of your framework yet?
So it's definitely still under active development, but some people have expressed interest and are trying to look at these things. So the general purpose secure computation frameworks I mentioned as well, they've been around for a while and it's been run through use cases. We're now trying to put this into the platforms, as I said. What we still see is that people come in with a use case and they take the model they already have in TensorFlow and they put it into this and they expect it to run with good performance. And we kind of have to help them a bit, saying, okay, but where can we tweak it to make it easier for you? And I think that's key before we can actually start to see real adaptation. For instance, here I was giving the model somewhat explicit by defining the layers in the network I was running through. What we're looking at as well is could we supply a more packaged solution where we're saying, instead of allowing, I mean, you could still do it if you want to, but then it's going to be your responsibility. But could we give you kind of a packaged model that we optimized for you, and then you can use and get better results? To not require this expertise of knowing how to tweak the model before you're ready for it, so to speak. So the interest in there, but
Yes.
it's underway.
Of course,
Yeah.
there is the-
Actually change the nature of the process.
When you talk, take the mic.
So the comment was that you're changing the.
But actually, you're changing the process, tweaking it. So at the end of the day, on marginal results, you'll get it wrong, maybe. So what is your experience? No, because you change the model. So in some cases, you won't identify the number in case of a noise or something because you've changed even the sigmoid. And you've changed some other aspect of it. So what's your experience on this?
So the comment is that would the models become useless when we move them in
Not
here?
users,
Because
but I'm saying that will be less effective. Like it will be, I don't know, maybe 90% instead of 99. Or that's what I'm trying to understand. What you have experienced right now.
I think you would be a good candidate for looking at the papers because some of them actually do give very. So they measure this as well. So performance is one measure, but accuracy is another one. And accuracy is roughly the same. There doesn't seem to be a big loss in this.
Not a big loss, but only in the hard cases probably. Or something. Hard to identify anyhow.
Or
I
in
don't
the
know,
case,
because
yeah.
it's non-linear.
in the test, in the data.
And also in regard to the convolutional networks, so there are also things that sometimes you want to see also the in-between results because it gives you a lot of knowledge. Like, for example, what part of the brain is processing it. It was found out to be more like the process itself. So sometimes there's also interest in the in-between stages, convolutional stages, and sort of if you change them, you might get a different results. So you are actually damaging part of the information, or you say, in this case, we'll tweak it again.
Absolutely agree. Yeah. So the comment is around how does it change the networks when we start to move it into the encrypted space, and there are some changes, no doubt.
Sure, some.
People do say we get good accuracy for this. Sometimes you need to take. I didn't make it very explicit, but you need to do. If you train using the ReLU, for instance, or using the actual sigmoid, and then doing prediction using an approximation afterwards, maybe you can have some issues there. But you can also train directly using the approximated sigmoid, and then maybe you get better accuracy. But there is an issue there, and I think this is just the first step in the direction of figuring out how can we have people with that kind of expertise help the cryptographers build these systems and answer these questions.
It's like a two-end game because, for example, in the AI area, there are a lot of things that that people didn't realize at first, and actually the convolutional was actually insight on how things are working. Sort of if they want to identify a larger group than what they've located at first, then the process of the output of the stages, not just the final answer, was actually the insight.
I agree.
And if you don't take this into account, and also maybe you have to encrypt this.
It is one thing. So again, doing this in TensorFlow is interesting because we can some of the tools that you would typically use for doing this and doing plaintext training. So kind of monitoring the individual layers and so on. What are the distributions that goes into a layer? We can somewhat quickly get the same thing. So we can say we run this, but then we decrypt in between each layer, and we can still doing training because we want to kind of inspect what distribution we have. Right. So that's another benefit of being in TensorFlow, that we get this entire ecosystem instead of having to rebuild it again from scratch if we start it from scratch. Valid point, definitely.
Thank you.